Unit 4. Applications of derivatives. Lecture 4.1. Modeling with derivatives. No questions at all, yeah? Okay. On we go. Up we go. Okay, we're going to talk about modeling with differential equations. We're going to talk about population models, a couple of other models, and then probably on Monday I'll do some sort of related rate stuff. Okay? Okay. Mathematical models of physical phenomena often describe relationships between quantities represented by functions and their rates of change, their derivatives. A differential equation is often what these models look like. Okay? Any model like that will be a differential equation. It's an equation that features an unknown function and some of its derivatives. Basically, scientific models are often more interesting than some of the models we've talked about so far. Okay, so like that sinusoidal thing isn't that interesting. Okay, if you want a more interesting model, you talk about dynamic systems. Dynamic systems are modeled with differential equations. And so we're going to talk about some differential equations. Okay. Here we go. Population growth models. Those of you in Biology 150 will see these there too. Okay, where do I write? First, we'll talk about exponential growth. Okay, so this is growth when what? There are no real constraints, okay? The environment doesn't constrain you, nutrients don't constrain you, disease doesn't constrain you, predators don't constrain you, okay? So everything's good. Maybe you've colonized a new habitat, maybe you're a bacteria happily living in a culture and you're in the exponential phase, whatever, and you have exponential growth. Okay, so we model up here. Okay, so the population dynamics are modeled by okay. dp dt equals kp. K is a positive constant. Okay, p is population, which is a function of time, and we're saying that its derivative is proportional to it. Okay? Which is something I've said repeatedly about exponential before. This is a differential equation. You've got a derivative and you've got the function in the same equation. Okay. We're saying the growth rate of the population is proportional to the size of the population. Yeah? Okay, I'm occasionally, or possibly all the time, going to write this thing without the t after. Okay, so remember all the time that p is a function of t. Okay? So if you prefer, you can write it in yourselves. Okay, I can rewrite this for non-zero p in this way. For non-zero p, I can write it that way. And what does that tell you? It tells you that the relative or per capita growth rate is constant. Okay? Again, the growth rate per individual in the population is constant. Okay? So either the relative growth rate is constant, or you say that the growth rate is proportional to the population. Okay. Okay, for the record, populations are sort of, they jump, okay? When you have someone being born, the population jumps, okay? So population isn't really a sort of continuous function of time. It's very discontinuous, and so it's not differentiable. And so what we do, instead of trying to model something that does this, right, is we sort of imagine a continuous curve drawn through it, and that's what we're really talking about here. Okay? All right. So we're going to pretend the population is a nice continuous differentiable function of time. Okay, is this sensible? Suppose you have no constraints, and suppose you have, let's say, bacteria or something. If you double the size of the population, you expect the growth rate to double, okay? Or in other words, you expect that if you double the population, the per capita growth rate won't change. That seems sensible, if there's no constraints on anything and nobody's killing anybody or anything like that, okay? Okay. All right, everybody, what's the solution to this going to look like? Okay, you're looking for a function that's proportional to its own derivative. Yep? And exponentials will do that. So, okay, let's say this. A solution of a differential equation is a function that satisfies it. Okay, so any function p that works in here is a solution of the differential equation. And as we just hinted or said, the exponentials solve this. So the general solution of this differential equation is of this form. Exponential growth. Yep? And there's no more growth rates here. This straightforwardly tells us what the population is as a function of time. Okay? Another way to think about this sort of thing is that if you know how the system works, okay, this models how the system works. Once someone tells you where you start, then you can simulate the trajectory of the system. Okay? So the solution is the sort of trajectory you follow. Okay? It's what happens. It's your prediction for the future, something like that. But mathematically, a solution is just something that works in there. Okay, let's check that it works. Okie dokie, what's the derivative of that thing? This is going to be very silly, okay? This guy comes out, it's a constant, e to the kt. Okay, we're going to use the chain rule here. Derivative of natural exponential is natural exponential, evaluated at inside, times derivative of inside with respect to t. The derivative of kt with respect to t is just k. And look, that's k times itself. Does that make sense? Okay? That guy works in that DE, so it's a solution. Okay, so exponential growth satisfies that, which I think is called the natural growth law or something like that. Okay? Okay, excellent. What is P0? If I evaluate that thing at 0, what do I get? P naught e to the k0. That's 0. E to the 0 is 1. P naught times 1 is P naught. So P naught is just the initial population size. Okay? Does that make sense? You sort of talking, yeah.
How on the previous whiteboard about the solution?
Yeah. Yes. How we got it we don't get it. So if someone, let's say someone tells you this magically, you can check it, yeah? Or someone more intelligently, you go, okay, well, what is it that is proportional to its own derivative? And you go, the exponentials are like that, so the solution might look something like this. Or if you know about integrals, this is what's called a simple separable differential equation, and you can do it that way, and that's how you actually get these solutions. Cool? In general. Good? Awesome. But for now, what did we do? I told you about the proportionality thing, and you know that exponentials have that property. Or someone magically told you this, and they just said, okay, now check it. Does this work in here? And you just took the derivative, made sure it was proportional to the function itself, and you go, yep, it checks. And then you want to interpret the model, so you see what is the population at size 0, and it's p0, so you know that that parameter just means the initial population size. Okay? All right. All right, what's that going to look like? Start at p0 and then grow exponentially. Cool? Questions, let me know. Okay. Yeah, again, your job isn't to solve these things at this point, okay? That's more advanced. Your job is to be able to check them. And to recognize what kinds of things are solutions to certain kinds of Ds. Okay, that was exponential growth. Now we do logistic growth. Are you guys there yet in 150 or no?
Yeah.
You are. Brilliant. So I don't have to do any of this. Okay, this is limited growth. The last one was unlimited. Okay. So the environment can't really sustain an arbitrarily large number of individuals, okay? Populations can sustain limited numbers. So, we'll call the maximum sustainable population size is called the, what's it called, people? Thank you. Carrying capacity. And I'm going to call it M, consistent with our textbook. I think you call it K. But we already have a K, and I would find that upsetting, so I'm going to call this M.
Yeah.
Okay? So that's what the environment can sustain. Okay. Give me a second. My refrain, if anything was weird or confusing or wrong, let me know. All right, here we go. So what do we want to do? Okay, so let's draw the relative growth rate of the population against the size of the population. Okay. If you're at the carrying capacity, you should stay there, okay? The environment sustains that. It doesn't want you growing or shrinking, okay? Death and birth will work out so that that happens. And so at the carrying capacity, you should have no growth, okay? If you're above the carrying capacity, death rate should be higher than birth rate, so that you come back down to carrying capacity. The environment can't sustain levels that high, it should bring you back down, okay? So if you're above the carrying capacity, you should have negative growth. Okay. Close to the carrying capacity, you should have a low growth rate. And all the way over here, we'll say that your relative growth rate, like before, is K. Little k. Okay. So that's what we're going to do. So again, let's see. If the population size is low or the population is small, okay, the relative growth rate is close to K. like before, the growth rate is essentially Does that make sense? Okay, so when the population is small, so we're down here, the relative growth rate is around K. Okay, so the growth rate is around Kp. So the growth rate is around proportional to the population size. Okay, which we said is what happens in exponential growth. Okay, for small population sizes, you essentially have exponential growth. When you're at the carrying capacity, you have no growth. When you're above carrying capacity, you have negative growth. And when your population is near the carrying capacity, the growth rate is around 0. Okay? Is any of that confusing? Okay. So all we need to do is write the equation of a line. Albeit in a weird way. 1 over p dp dt. Okay. Okay. Yes, yes, good. Okay, that is the equation of that line. Okay? All good? All right. So we came up with a reasonable model. We rewrote it like this, and let's in fact rewrite it like this so it even works at p equals 0. Which is something you may have seen already. Okay? This is the logistic growth model. And that sure is a differential equation. Derivative and the unknown function. Okay? Model, write the equation for the line, rearrange a bit, and that's it. Okay.
K, like K is just like a
It's a parameter.
Yeah.
Yeah. And at the beginning, the thing behaves exponentially with parameter k.
Right.
Like before. Yeah. At the beginning, I mean for low population sizes. Okay? All right. All right. I'll draw this graph in case this illuminates anything for anybody. We did the relative growth rate there. I'll just do the growth rate here for the record. The growth rate looks like this. This guy is, when p is 0, this guy is 0. When p is m, it's 0. And in between, it's a downward parabola. 0, m. And its maximum is predictably at m over 2. Okay, so if you want to think about relative growth rates, you think about this. If you want to think about growth rates, you think about this. Okay, not as functions of time, but as functions of population size. Okay, again, make sure everything works in here. Okay, when p is small, okay, and particularly when p is small relative to m, okay, so when p over m is very small, much smaller than 1, this is approximately equal to 1, so this whole thing is approximately equal to kp. Just like I said over here. Again, if p over m is much smaller than 1, then 1 minus it is approximately 1, so kp times approximately 1 is approximately kp, which is all I said here. Okay? Just verifying what we said here. If you put p equals m in here, you'll get 0. If you put p equals 0 in here, you'll get 0. If you put p greater than m in here, you'll get something negative. Okay? Everything's consistent. Okay? Do whatever checks you need to do to convince yourself this makes sense. All right? So P is small, you could think of that as P much less than the carrying capacity. Good? All right. Okay, so both that natural law we talked about before, the exponential one, and the logistic one can be handled by the methods used. Okay, so if you know about integrals, these are both separable. You don't have to write this down. These are both separable differential equations, okay? They're relatively easy to solve. The other one's much easier than this one to solve, but they're relatively easy to solve. So if you care about it and you know about integrals, you can have a look at that and try. Or ask me. Okay? So that's how you solve these things. But again, it's not your job here to solve. Okay, let's see what the solutions look like. You don't need to know that equation. You don't need to know where it came from. You don't even need to check it. Okay, so these are some solutions for different values of k. Okay? What do we got? Okay, here I've got population size as a percentage of carrying capacity, and here I've got time in years. And what can you see? You can see initially the growth is exponential looking, and then as you get close to carrying capacity, which is 100%, it slows down. Yeah, which is what we talked about. And as time goes on, you just approach carrying capacity. Okay? This is called the sigmoidal curve. It's S-shaped. And k does what you'd expect it to do given this equation, for instance. Okay? As k gets higher, okay, so if you have a system with a higher k, everything's going to be faster. If you go lower k, things are going to be slower. Okay? Or you can think of k again as being a sort of compression factor. Okay? As you bring k up, this thing gets squeezed this way. Okay? Kind of like on the midterm with that tree thing. Okay? All right, does that all make sense? Okay, so what did I do here? I started at 1% of carrying capacity, and then I used whatever magic I know about to simulate these things, okay, or draw these things. Okay. And again, as time goes on, in case you feel like writing this, as time goes on, the population approaches the carrying capacity. Initially, you go around exponentially, and then as you get closer to carrying capacity, you grow slower and slower and slower, just approaching the carrying capacity. Okay? All right. Okay, so let's look at some other initial populations and see what happens, okay? If you start at 0, you stay at 0, okay? You can't make babies out of nowhere. So if you start at 0, you stay there. This is the one we already had, okay? So we sort of grow sort of exponentially, and then we slow down as we approach carrying capacity. That was starting at 1% of carrying capacity. If you start at 10%, you get this curve. If you start at 50% of carrying capacity, you get this curve. If you start at carrying capacity, you stay there, okay? And we designed it that way. If you start above carrying capacity, death rates are higher than birth rates, you get brought down to carrying capacity, because that's all the system can maintain, okay? Okay, so what the curve looks like, the particular solution depends on where you start. And note, down here in particular, that whether you have an inflection point, if you know that is, whether you have an inflection point or not in this depends on where you start. Okay, so if you start here or higher, you're not even going to have an inflection point. In case you care. Okay, any questions about any of that? Again, it was just the same thing as before, down here. Okay, you approach. If you start here, you stay there, and if you're above, you descend toward. Okay, and there's no way of overshooting in this model. There's no way of beating carrying capacity and then coming down toward it. That doesn't happen in this model. Okay? Okay, if you're bored, stay bored. I'm going to say some more stuff. This is mathy stuff. You don't need to know this. Okay? I said if you start at 0, you stay at 0, because you can't make babies out of nowhere. If you start at 100, you stay at 100, because by design, if you have carrying capacity, that's what the system can maintain. Those things are called equilibria, or steady states, or fixed points, okay? Where if you start there, you stay there, okay? And in particular, this guy is called an unstable one, okay? Or a source, or a repeller, because if you start near it, you run away from it, okay? This is called an attractor, or stable, or a sink. Because if you're away from it, you get drawn toward it. Okay? That's for the mathier types. But don't worry about any of that. Okay? Just know what those shapes are. Make sure it makes sense to you. Okay? All right. A couple of variations on the model. If you want to include, I think you've seen this on the biweekly, right? Something like this?
Yeah.
Is it okay? Possibly all of this. To include immigration at a constant rate I, so if you, I don't know, add to the population in some way or another, I individuals per unit time, or emigration or harvesting, so you pull out E individuals per unit time, then you can change the model like this, right? Quite straightforwardly, you have the logistic guy here, this was a rate, okay? So you just up the rate by I and reduce it by E to model immigration, emigration at constant rates. If you pull out KE, if you pull out KE individuals per person per unit time, then you have something that looks like that. Okay? So for each person, you suck out KE people per unit time. Okay? So you can just change these models and probably make them harder and harder to solve. Okay? So you got the basic logistic one, and then you have variations on it by modifying various things. Any questions about that? Okay. All right, guys, now that you know about derivatives and DEs, I will show you examples throughout the term of various kinds of DEs, and I'll pick stuff that's applicable to biology and physiology and stuff. For now, still in physics land. Any questions about anything?
Did we have to like memorize those last equations?
Which one?
The ones about like immigration and immigration.
I say understand them. You should be able to reproduce that. So if I say, and we don't even, probably not even, but you should be able to reproduce it.
Okay.
Given what's that?
Reproduce what exactly?
So okay, someone says that you're putting in I individuals per unit time. Then you should know that what are you doing to the rate? You're adding I onto it. That's it. Right? That should make sense. Okay? Now the odds of us actually putting that on a test, you've seen what our tests look like, so judge for yourself. Okay? Is that a reasonably okay answer? Okay. All right, where am I? Yeah, make sure that those make sense. And as soon as they make sense, you should be able to reproduce them right away. And if you can't, let me know. All right, other examples. Mass on a spring. Okay, which is an example of a simple harmonic oscillator. So what have you got? You've got a spring hooked up to a mass. The spring has constant K. And I think you've seen this on the biweekly as well. Yes? Or something like this? Or maybe you'll recognize it shortly. Okay. The net force at time t acting on this mass. Okay? We talked about Hooke's law. Okay? It's a resisting force, hence this minus sign. Proportional to how far the mass is from equilibrium. Okay? So this is the net force acting on the mass. Don't worry too much about this. It's the net force acting on the mass, and it's in opposite direction and proportional to how far you are away from equilibrium. Okay? So as you come down, it pulls you up. Okay. So that's Hooke's law. Newton's second law tells you this, that the net force is mass times acceleration. Our buddy Newton. Yeah? Okay. So m times acceleration is equal to minus k times position. And that gives you that differential equation. Okay? Hey look, we have a second derivative now. Okay? The second derivative is in the opposite direction too and proportional to the position. Okay? What kind of function do we know of that does that? Okay? Whose second derivative has opposite sign to and is proportional to it. And the answer is sinusoids. Excellent. So, the general solution is this. The specifics of this you obviously do not need to know. if I gave you this, you should be able to verify it. You should be able to differentiate this twice, okay, and check that that satisfies that differential equation. Okay, that you should be able to do. And I think you may have done something like that on the assignment. Okay. Notice we have three parameters here. These guys are specified by the system. These are specified by this business, okay, these guys. But A and phi are, you could write that like this, you could write that like this, that thing. Okay, these are free parameters, okay? They're like that P naught in the other thing, right? They're like P naught in the exponential model, okay? They're free parameters. They're determined by the initial conditions. So in the other case, what do we say? P naught was determined by the initial population size, okay? Here, these guys are determined by, for instance, how fast you're moving initially and where you are initially, okay? So, these are determined by the system. These guys are determined by, for instance, how you start, okay? Where you start from, for instance, okay? Solving for these guys is kind of like how you guys solve for A and B or something on the midterm, okay? Someone gave you some information and then you solve for these guys, okay? So for instance, if someone tells you that the spring constant is 500 newtons per meter and the mass of the object is 500 grams, and they tell you that initially your position is 15 centimeters and you are moving at 2 meters per second in the positive direction, then you can construct a particular solution. Okay? And if you want an exercise using that, and that, and that, try to come up with the A and phi that satisfy it. Okay? If you want. And that's the particular solution. And that's the graph of that particular solution. And as you can see, that thing satisfies everything. That thing satisfies the initial conditions. We do indeed start where we said we'd start, and we do indeed start at the speed we said we'd start at, or the velocity we said we'd start at. Okay? Okay, so someone gives you a DE, you get a general solution, then they tell you where they started at, and then from there you can get exactly the particular solution, exactly what the trajectory is going to be over time, according to your model. Okay? Okay. We are done, guys. I'll continue from there next time. Have a wonderful weekend. I don't know how lost you were when we talked about the differential equation stuff. So let me have a quick chat about that. Okay, so what did we do? We talked about three examples. We talked about two population growth examples, exponential and logistic, and we talked about the mass on a spring, okay, which follows the simple harmonic law. Okay, so what was the first step that we did? We built a differential equation model, okay? And that comes from observations, natural laws, assumptions, whatever. So based on a bunch of things, we build a differential equation, okay? I haven't posted this yet, I'll post it if you want me to. Okay, so for the exponential growth model, we have this, which is called the law of natural growth, and we'll talk about that again today. Based on a bunch of assumptions or things we've seen, let's say, bacteria do or colonizing populations do, okay? And here we have the law that the rate of change of the population is proportional to the population size with a positive proportionality. And then we thought, well, that's not very realistic in all situations, so let's try to make that a bit better. So we came up with a logistic growth model. And basically what we did here was that we said that the rate of change of the population for small population sizes is the same as this. But as we get bigger, we approach the carrying capacity, and at the carrying capacity, the rate of growth is 0. And again, I'll talk about some of that in tutorial. So that was the logistic growth model, again, based on some assumptions and things that seem reasonable to us, and checked by observation. This one's different, it's got nothing to do with populations, necessarily. And we talked about mass on a spring, and we modeled it using physical laws, Hooke's law and Newton's law, and using that we built a differential equation model, which in this case has a second derivative in it. And that's it. So you build a differential equation model to see how something works. It could be a population, it could be a circuit, it could be the motion of the planet, whatever. Something you want to understand the dynamics of, you build the differential equation model to describe its dynamics. And then you solve it. You do not need to know how to solve it. I think I know how to solve them, yeah, okay. You don't need to know how to solve them. What you do need to know this one, and we'll talk about this again today, so this better be inscribed on your heart by the end of today, or at least by the final. So you should know that the natural growth law leads to this thing. That proportional growth thing leads to this, exponential growth. The logistic growth solution is this, everywhere but 0. Do not worry about this at all. And the simple harmonic oscillator solution is this. You should be able to verify that this and this satisfy the DEs we just had, okay? So you should be able to take the derivative of this and see that it's proportional to it. You should be able to take the second derivative of this and see that it's equal to minus k over m times that, okay? Basically, be able to verify that these are solutions, but you don't need to find them. That would be great. Although these are particularly nice things to solve. Okay. Notice that each of these specifies a family of functions, not just one function, okay? Because there's 3 parameters in here. Okay, so you don't just get one function, you get a bunch of them. And what is a solution? A solution is a trajectory, okay? A reenactment, a projection, a simulation, okay? It's how you expect things to happen over time, given the differential equation you have. Because you might think, well, this is a bit of an opaque model, I want to see what actually happens over time. So a solution is what happens over time, okay? Or over space, if your variable is space. What else do I want to say? Okay. You can still get nice solutions from there, or sorry, nice information from this, despite the fact that there's 3 parameters, despite the fact that you're actually talking about a family of functions. For instance, in most cases here, you have exponential growth. Okay? You have certain trends here that we talked about, and we'll talk about again tonight. And over here, you know, given the mass of the mass and the stiffness of the spring, you already know what frequency this thing is going to jiggle at. Okay? And hopefully you guys know what this was. Okay? You have a mass on a spring, it goes bouncy bounce. Okay? And this is saying the position with respect to time. Okay? And just given the stiffness of the spring and the mass of the object, okay, you know how quickly that thing is going to oscillate. It has nothing to do with where you release it from or how fast you release it, which is interesting. Okay. Does that make some sense? Okay? The solutions are the trajectories you expect given the differential equation model. And finally, if you know where you start from, then you can pick one of those trajectories. If you know the initial population, you fix that parameter, and you have exactly one, let's say, projected trajectory or simulation or reenactment or whatever. Same with logistic growth. If you know the initial population, you fix that parameter, and you get exactly one curve, okay? That tells you what you think is going to happen over time. With the mass and the spring, you need 2 initial conditions, okay? Because there's a second derivative in there. So you need 2 initial conditions. If someone tells you where they let the mass go from and how fast they let it go, then you can figure out what those A and phi were, and you get exactly one trajectory that tells you over time how this thing is going to move. Okay? Okay. So for people who say, well, differential equation isn't that enlightening, I want to see what actually happens over time. The solution tells you what happens over time. And some of these things you do with a computer. So you just give the computer the differential equation model, you tell it where to start from, and then it just does what a physical system would do, and it would try at least to simulate approximately what would happen. Okay? So a computer would sort of skip that second step, and it would jump right to the final solution. I don't know if that's enlightening or makes things more opaque. Do you have any questions about that? Okay, again, nothing obscure. You have a dynamic system, you model it, you solve it, and you see what happens over time. If you understood some of that, that's good enough. Okay. Okay, we were talking about the mass on a spring. We made up a differential equation model, and I'm using Newton notation for the second derivative there. I said, suppose we had this stiffness and that mass. Suppose we started at that position, and the mass started moving that quickly in that direction. And from that, we can solve for A and phi, and we get that particular solution. Okay? So that's what we expect to happen over time. This thing goes bouncy bounce with the right angular frequency, that amplitude, and that phase. Okay? And as you can see, it satisfies the initial condition I gave it, both in terms of position and in terms of velocity. Okay? Okay. Now, that's a position time graph. Any questions about this or what I said before? Okay. Okay, so these are position, velocity and acceleration graphs, okay? So position, first derivative, second derivative. Check that the units make sense to you. This is exactly what we had on the previous slide. And make sure that the sort of derivative relationships make sense, okay? First of all, you can notice that this guy looks like this guy flipped and stretched, which makes sense, because what did we say? We said x double dot is equal to minus something times x. Okay, so this guy better be a stretched and flipped version of this. And it is for every single harmonic oscillator. What else have we got? Where this guy is changing fastest, we have a maximum in the velocity. Good. Where this guy has a horizontal tangent, or is momentarily stationary, we have zero velocity. That makes sense. Okay? So make sure that the signs make sense, and the zeros make sense, and everything increasing, decreasing makes sense. Okay? Okay. All three of these things describe motion, almost interchangeably. Some of you will know that you can't exactly get all of this information from this immediately, and you can't get all of this information from this immediately. Okay, but roughly they represent the same kind of information. But each of them tells you about a particular aspect of the system. Okay? For example, you'll know that the kinetic energy of the mass is proportional to the velocity squared, or sorry, the size of the velocity squared. You'll know that, possibly, the potential energy in the spring is proportional to the position, or the displacement squared. Okay? So while they are roughly almost interchangeable, and they all describe position, each of them describes an important different aspect of movement. Again, so for example, if you care about the potential energy in the spring, you probably care about this directly. If you care about the kinetic energy of the mass, you probably care most directly about this. Okay? They all tell you about motion, but they tell you about different aspects that you might care about more in different contexts. Any questions? Okay. Almost out of the blue, almost nothing to do with the rest of this lesson. We'll talk about related rates briefly here, and then in the tutorial I'll do some examples. Related rates. Where we will see the chain rule a lot, especially today. Okay, so what we do here is we identify via an equation or something relationships among two or more quantities then determine the relationships among their rates. Okay, so you write down an equation. Okay, you write out an equation that tells you how a bunch of things are related, functions are related, and from that you find out how their rates with respect to time are related. Okay? Hence related rates. So for example, if there's something that's easy to measure, or its rate is easy to measure, then you can determine the rate of something that's less easy to measure from that. Okay? If you can relate their rates. Okay. Alright, this is a particularly benign example. We'll do a few more tutorial. Here we go, ideal gas law, because you all were so happy last time I said this. Related rates in the ideal gas law. 3 moles of an ideal gas are held in a sealed chamber. If the volume of the chamber is 10 liters and increasing at 0.3 liters per minute, and the gas temperature is 300 degrees Kelvin and increasing at 2 degrees Kelvin per minute, what is the rate of change with respect to time of the pressure of the gas? That's the ideal gas law, P equals nRT, which you've seen several times here, and I hope many times elsewhere. P is pressure in atmospheres, V is volume in liters, N is the amount of gas in moles, T is the temperature in degrees Kelvin, and R is the ideal gas constant. And consistent with those units, we'll use that number. Okay. Drink time. That's very sweet, thank you. Okay, here we go. That example. All right, we need to come up with an equation that describes the relationship between the variables. Okay, already someone has kindly given us the variables and the symbols for them, and someone's already kindly told us what the relationship is. Okay, so that thing, this identify relationship step, and all variable declarations and all that stuff has already been done for us. PV equals nRT. Okay. I'll rewrite this as P equals nRT over V, or nRT V reciprocal. You can do it with this unmodified as well. If you want, try it, and you'll see why I found it a tiny bit annoying. Okay? So you can do it from here, but it's just slightly smoother doing it this way. Just slightly. Okay. And plus, I think I forced chain rule doing it this way, so that's nice. Okay. What do we know? Given constant. Obviously, the ideal gas constant is constant. I don't remember this anymore. Okay? And the number of moles was 3. And we said sealed chamber. And I said that so you know that the number of moles isn't changing. Okay. All right, those were constants. They don't change over the course of this thing. Given instantaneous. Okay, I'm spelling this out to be clear. If you want to do problems without spelling stuff out, that's fine too. Okay, so I want to know what's given at the particular time of interest. Okay, these could be variables, but at the time of interest they're specified. So we're told that the volume of the chamber is 10 liters. We're told that the volume of the chamber is increasing at 0.3 liters per minute. Okay? Rate of change of volume with respect to time. We said volume is increasing, so you better have a positive sign there. Okay? And by the way, time I'll do in minutes, consistent with what I've been given. Okay. What else have we got? We've got the temperature is 300 Kelvin. And we've got the rate of change of temperature is 2 Kelvin per minute. Again, increasing, so positive 2. If it was decreasing, you'd have a negative there. Okay. Unknown. At the instant of interest, I want to know the rate of change of pressure. Rate of change of pressure. Okay. Again, the quantities we're interested in are related to one another. We want to know that rate, so we better relate it to the other rates and the other quantities. Okay. Here we go. Differentiate both sides with respect to t, because we want what? The rate with respect to time. So, ta-da. Okay? All right, derivative of p with respect to time. I'll just rewrite that. N and R, we said what? We said they're constant. Okay, so we can bring them out. Okay? You could have done this with sort of quotient rule if you wanted to. Okay, now what have we got? We've got a product, so product rule. If you have trouble with the intermediate step, or I will in a minute, let me know. Okay, so the derivative of the first guy. So derivative of temperature with respect to time times the second guy. v reciprocal. Plus the first guy times the derivative of the second guy. Okay, here's where I'm forcing you to use chain rule. Derivative of the outer function, you bring the minus here, you reduce that guy by 1, and you wind up with minus v to the minus 2. So, minus v to the minus 2. That was the outside function. There's an inside function. V is a function of time, and we're differentiating with respect to time. So, by chain rule, we multiply by dv dt. Okay? Alright, so what we did was we took the equation we had, differentiated with respect to time. And r, I'm just rewriting now. There we go. Make sense? Alright. And now let's plug in. And we'll be done. 3 times 0.0821. Rate of change of temperature was 2. Volume was 10. Minus rate of change of volume was 0.3. Times temperature was 300. And volume was 10, and we square that. Okay? And then you use your calculator to get minus 0.172. And what are the units? Time was in minutes, pressure was in atmospheres, so if you need to say units, this would be in atmospheres per minute. Okay, so if you need to interpret this, what's happening? The pressure at that instant is falling at 0.172 atmospheres per minute. Okay? All right, these were constants. You could have plugged them in all the way up here. Okay? That's fine. You can take the constants, plug them in here because they're not changing, okay, with time. The instantaneous guys, you can only plug these in after taking the derivative. Okay? These things that describe how things are moving and what values things have, okay, at the instant of interest, you can only plug these in after taking the derivative, okay? If you plug these guys in before taking the derivative, okay, you get a bunch of constants, it freezes the picture, and your derivatives are going to end up being 0, okay, which is nonsense. Do not plug these things in before taking the derivative, okay? And that's it, okay? Relate, it's a lot of marks there. Okay, relate the quantities. Tell us what you know and don't know. Differentiate with respect to time. To relate the rates. Use chain rule if necessary. Sometimes not really necessary. Tonight it will be. Plug in, get your answer, and that's it. Okay? And if you need to interpret the answer, interpret your answer. Okay? Glad you're quiet today, people. Again, I picked this because it's a fairly benign example, and also it's got this thing, which we've seen before. I'll do more involved, more chainy stuff tonight. Okay? Any questions? Seriously. Someone give me a nod. Does it make sense? Okay, good. All right, thank you. Okay, excellent. That's that lesson done. That was modeling with derivatives. We will now do exponential processes.